So in the previous part, we introduced the concept of links, which is just a generalization of knots to more components. Now we will start with our first knot slash link invariant. So I'll first explain the general idea of an invariant. So I'll use the example of knots, but really invariance is a very broad subject and it's applied to almost every branch of mathematics, but I'll explain it through the idea of knot theory. So what an invariant is basically for every knot, I will assign a number or like a polynomial. So there are numerical invariants and there are polynomial invariants. So I'll just stick with numerical invariants right now. So for each knot, we will assign a number in a certain way, such that whenever we change the knot, the number remains the same. So for example, trefoil knot might have number 1, and however we change the trefoil knot, the number will still remain 1. And it'll be some algorithmic definition, like we take each of the crossings, do some numerical jugglery with that projection, and we'll get some number, and it turns out that that number will remain the same through all projections. And we will design that number in certain ways so that it will always remain the same. So let me explain the logic. So two different knots could have the same number. As of this day, nobody has found an invariant such that given any two different knots, they will always have different numbers. Any invariant we know today, you won't find two different knots with the same number. But if you have two knots with different numbers, those two knots must be different. Because if they were the same, they would have to have the same number. So if they have different numbers, they must be different knots. It's a little bit, you can try to understand that. Like, same knot implies same number, so different number implies different knot. But same number does not imply same knot. It's like a concept in logic, so you can like pause the video and think about what I just said and try to understand that, and then we can move on to the actual invariant. So now, once you've understood that concept, let's go to the idea of linking number. Okay. So for linking number, what you want to do is, so linking number will only work for a two-component link. You want exactly two components. And linking number is only defined for those. And what you want to do is you want to orient both links. So you want to put a direction on both components. Now we will look at what is the sign of a crossing. Let's see what that is. So let's say you have one strand, which is the arrow. So its direction is this. And then you have another crossing, another strand whose direction is this, and they cross. This crossing is denoted +1, and I'll show you how to remember the sign. There's the way. And this one is called -1. So there are two ways you can remember. So one of them is using the so-called right-hand rule. This is used everywhere. So what you do is you align your right hand with the over strand. You rotate it to the under strand. Then for +1, your thumb will be pointing out. That means +1. In this case, you need to orient like this, like that. Your thumb is pointing inward, so you have a -1 crossing. But then another way to think about this, which might be slightly easier or less easier, this depends on what you like, is to think about it like this. Imagine taking the over strand. Imagine taking this as like a hand of a clock or something. To rotate, to make this match up with this one, what direction do we have to rotate? It's counterclockwise. If you think about it, to rotate this strand to this strand is a counterclockwise rotation. The over strand to the under strand. But here, to rotate the over strand to the under strand is a clockwise rotation. And generally in mathematics, we always prefer the counterclockwise direction over the clockwise direction. And so the counterclockwise direction is given a sign of +1, and the clockwise direction is given a sign of -1. So that is the concept of sign. Now let's see what is linking number. So let's say the link is made up of two components, M and N, and they are linked in some way. Then, so we write the linking number L of M comma N is equal to half times sum of signs of M and crossings. Let me explain what this means. So forget the half factor for now. So each crossing in our link will have a sign. We just explained how that can be, how we can find the sign of each one. Now you sum over all the crossings. You don't sum over all crossings, sorry. You only sum over the crossings which are between M and N. So let me just give you an example right here. Let's see. I don't know, I'm just going to add an extra crossing in here. Like that. So, and we put some orientation on these, because sign always needs orientation. Then we only consider this crossing and this crossing. Since this crossing is an internal crossing, we ignore it. We only sum over the M N crossings, which are the crossings between the two different components. And we always have to take the factor of half. So let's see an example. Actually, before we see an example, let's think about this. We could have chose the directions differently, right? So basically what I want to see is what is, so M bar is basically changing the direction of M. We saw that in the previous part, actually in 2 parts before. M bar is just a reverse orientation. So what is this in terms of this? Well, each MN crossing, so let's say before you had a crossing like this. This is a -1 crossing, and this was the M component, and this was the N component. Now if you switch direction on this one, since before it was a -1, now you can align your hand like this, rotates like that, hand points outward. It's a +1 crossing. So now the sign changed from -1 to +1. So whenever we change the orientation on exactly 1, all the signs will change. So if every single sign changes and we sum over all of them, the whole linking number will become minus. So this will be minus L of Mn. And similarly, if we change direction on N, we will have minus L of Mn. But now let's see what happens if we change direction on both. Now one way to see this is using the picture. So before this was a -1. But now let's see. Now we start off like this, go like that, from over to under, hands pointing inwards. This is a -1 crossing. So before it was -1, we changed both directions, it's still -1. We can do the same thing for +1. So changing both directions, each sign remains the same, so the linking number remains the same. Another way to see this is by seeing that L of M bar N is minus L of Mn. Now again, taking bar of this, so then this, let me just write out the algebraic way of doing this. This is minus L of M N bar, right? Because of this. And again using this is minus of L of Mn. And that is just L Mn. So thus changing both orientations preserves the linking number. So that way if you wanna forget about orientation, there's only one. If you wanna forget about orientation, you have to take the absolute value of the linking number to get an invariant. Now we will continue the discussion in the next part.